Hello everyone, I welcome you all to this course on experimental nanobiotechnology. Myself, I am Gopinath, professor in the Department of Biosciences and Bioengineering and also a joint faculty in the Center for Nanotechnology. The title of today's lecture is Synthesis of Nanomaterials Using Ball Milling. In today's lecture, we are going to learn what is ball milling, what is the principle of ball milling, and what are the various types of ball milling, and we will be also learning ball milling process parameters. At the end of the lecture, through practical demonstration, we will learn this ball milling technique more in detail. Before I talk about what is ball milling, let me briefly explain what is nanoparticle. Nanoparticle means any material which is having at least any one of its dimension should be in the range of 1 to 100 nanometer. And the word nano is a Greek word that means small. And most of you know the nanometer means it's a 1 billionth of a meter, that is 10 power minus 9 meter. Let us see the classification of nanoscale dimensions. Zero dimension means materials having all the dimension x, y, z within nanoscale, that is less than 100 nanometer. Examples are quantum dots, nanodots. One dimension material means it has two dimension at nanoscale and the remaining one dimension is larger than 100 nanometer. Examples are nanotubes, nanowires. Two dimension material means it has only one dimension at nanoscale and the remaining two dimensions are larger than 100 nanometer. Examples are nanofilms, nanocoatings. 3D materials are not nanomaterials because none of the dimensions are at nanoscale. It means all the three dimensions are larger than 100 nanometer. Examples are bulk powder, diamond. So, how to make this nanomaterial? There are two approaches. One is top down approach, the other one is bottom up approach. The top down approach is like building something by starting with a larger component and carving away material like a sculpture. The simple example for understanding this concept is from the rock you are making the statue. From a very big size you are making the nano structure. So, that is top to down approach. For example, from the bulk you are making the nano material. So, this is called top down approach. From a very big size you are going to reach nano size. And the next approach is bottom up approach, that is it's like building something by assembling smaller components like atom by atom assembly. The simple example for understanding this concept is using a brick and constructing a building. And most of you know the amino acids are the building blocks for the proteins. And if you see the size of each amino acid, so these are in the range of angstrom. And these amino acids combines and form the nanoscale protein. And most of you know the DNA is made up of nucleotides, that is A, T and GC, and the size of each nucleotides are in the range of angstrom, and these nucleotides combines and form the nanoscale DNA. So, from a very small size you are reaching to the nanoscale, so that is called as bottom up approach. And whenever we talk about nanomaterial, whenever the size goes down, the surface area to volume ratio will be higher. So, let me explain how this surface area to volume ratio will go higher when the particle size goes down. So, let us see a simple example. You take a 2 mm box and cut this same 2 mm box into small pieces of 1 mm size. So, this is like your bulk material and this is like your nanomaterial. And apply the surface area formula, then you can calculate, you can see that the surface area is more for your nanomaterial, but the volume will be the same. And when you calculate the surface area to volume ratio, the surface area to volume ratio will be higher for the nanomaterial. So, that is why whenever the particle size goes down, the surface area to volume ratio will be higher for the nanomaterial. So, these nanoparticles can be prepared by various methods like physical method, chemical method and biological method. So, today we are going to learn how to make the nanoparticles by physical method, and these physical methods involve breaking down larger materials into nanoparticles. It can be through mechanical force or it can be through the energy based process. And some of the common examples I mentioned it here. You can see this under this mechanical method ball milling technique is there. Today we are going to learn this ball milling technique. And there are several other techniques, energy based, physical vapor deposition, laser ablation, ion sputtering, and arc discharge. And in today's lecture, we are going to learn ball milling technique more in detail. This ball milling is also known as mechanical mill or pebble mill or tumbling mills. And this ball milling technique is a top down process, because from a very big size we are going to make nano size material, and this is your bulk material, and here we are going to use these balls. That is why it is called as ball milling. So, you will be using these balls and breaking the bulk material into nano size material. And this ball milling is a cost effective technique, and it is a eco friendly green technology, because we are not going to use any toxic chemicals for preparing these nano materials, and at the same time it will not consume much energy. So, that is the advantage of this technique. So, what is ball milling? Ball milling is one of the powerful technique for reducing the particle size to the nanoscale, and here what happens is the particles which you want to break, the powder, so that will be trapped between the two colliding balls, and when it's the particles are trapped, and it's keep on mill it and make the powder to reduce the particle size to nanoscale. And what is the principle of this ball milling? The principle of ball milling is mainly based on attrition and impact. So, what is attrition? So, attrition where the balls rub against one another. Okay. So, the balls will be rubbing each other, and then it makes the powder to reduce the size to smaller size. And impact. So, what is impact? So, when the ball milling is rotating, what happens is, so these balls will be taken to the top due to the centrifugal force, and it will fall down along with the powder, and it breaks the powder, and that leads to reduction in the particle size. So, that is the impact. So, the principle of ball milling is mainly based on impact and attrition. So, attrition means the balls are rubbing against one another and the material being ground, and in impact is the balls are taken through the centrifugal force to the top, and it will fall down, and it will break the powder and reduce the particle size. So, what are the various types of ball milling? So, broadly we can have it like 3 types, that is horizontal ball milling, vertical ball milling, and planetary ball milling. So, in the horizontal ball milling, it is a continuous process, and it is mainly suitable for larger quantities, and it can be also used as a kind of batch process also. And in the vertical ball milling, it generates less heat, and it is mainly useful for wet grinding. For example, if you are using some solvent, you can use it. The vertical ball milling is one of the important technique. And the third one is the planetary ball mill. It offers a high energy milling through the complex orbital and rotational motion, which I will explain detail in my subsequent slides. So, let us see what is horizontal ball mill. So, horizontal ball mill is a cylindrical grinding equipment, and again as I explained earlier, the ball milling principle is based on impact and attrition, and when the mill is revolving, the grinding media, that is the balls, the grinding media is balls. So, that will be lifted by centrifugal force and cascading down to impact and grind the material. So, it is lifted to the top by the centrifugal force, and the balls will fall down and break your powder into nano size material, that will reduce the particle size. And this horizontal ball milling mainly useful for continuous processing. So, we can add the feed material on one side, and we can collect the final product in the other side. So, in this picture you can clearly understand. So, you can feed the material here, and we can collect the final finished product by using these adjustable discharge slots, and the dust will be collected from the top. So, the next type of ball milling is vertical ball mill. The primary principle behind this vertical ball mill is centrifugal force generated by the rotating drum. As the drum spins, what happens, the grinding media, that is the balls, so that will be lifted against the drum's inner wall, and this creates a cascading effect, and the balls fall back onto the material, and that leads to the material will be broken into small size, and that leads to the reduction in the particle size. So, you can see here, and the balls will be lifted to the top, and it will fall back and it will grind the material. So, the advantage of this vertical ball mill is we can also use the liquid media, we can also use the solvent. So, when you use this solvent, so it will be also useful for wet grinding. So, that is the advantage of this vertical ball milling. And the next technique what we are going to learn is planetary ball mill. So, this ball mill consists of one or more grinding bowls. You can see here there are more number of grinding bowls and that rotate around a central axis while simultaneously revolving on their own axis. So, this base will rotating in this direction and the bowls that will rotate in the other direction. So, you might have also played during your childhood this cup and saucer ride. So, it is similar to that. So, you can see here, so the base is revolving in this direction and you can see this each cup it also revolving on its own axis. So, the planetary ball mill principle is similar to that. So, the grinding bowls moves combine with the rotational and orbital motion. So, which will create a high centrifugal force and which leads to result in intense impact between the grinding balls and the material. So, that leads to the reduction in the particle size. So, in this slide you can clearly understand. So, the rotating spindle is rotating in this direction and the central main disc which will be rotating in this direction, you can see this will be rotating in this direction and this grinding bowl rotating in counter direction. So, this bowls will be rotating in this direction. From this slide we can understand the rotation of grinding bowl in this direction and the supporting disc in the other direction. So, what happened due to these centrifugal force, the balls along with the powder material will be lifted and will be taken to the other side and it will be repeatedly hitting the vial content. So, which leads to the reduction in the particle size. So, next we are going to learn the various ball milling parameters and how these ball milling parameters will affect the final product, the size of the final product. And under these ball milling parameters, we are going to learn the container material, milling medium, rotational speed, BPR ratio and milling duration as well as the vial filling volume. So, let me explain one by one in detail. So, the first parameter in the ball milling technique is container material. So, the container material is very important parameter. So, we have to select the right container based on our material. So, then only the final product we can get it in a smaller size. So, for example, if you are using the high purity natural agate, so which is a chemically resistant. So, this will be very useful for materials where you want to use this acids and solvent. So, in this case we can go for the high pure natural agate material. And if you want to work on non-stick properties of the material or if you want to reduce the contamination, so the ideal choice is Teflon container. And we can also use the stainless steel container, depends on the final application. If it is for metallurgy and electronics application, we can go for grade 304 and if it is for the food and pharmaceutical application, we can go for the grade 316 and 316L. And the next important parameter is the ball milling medium, that is the ball. So, the milling medium is the ball and we have to select the right balls for the correct material. So, then only we can get the particle size reduction without any contamination. For example, we have metallic grinding media, that is the metallic balls, so which will be mainly used by most of the industries and this metallic grinding balls it will be useful for breaking the hard surface materials like hard materials. So, it can easily break the hard materials and some cases we have to use this non-metallic grinding media. For example, if you are working on a polymer or if you are working on a biological material and you want to avoid contamination, in this case we can go for non-metallic grinding media. So, how to select the correct milling media, that is the correct balls for our ball milling technique. So, that is very important. So, the first point is density. The milling media, that is the milling balls with the greater density will produce the fine particles. So, we have to make sure that the gravity of the medium should be greater than the milling material. And the next one is the particle size. So, the size of the media impacts the milling efficiency. So, the media is it is balls. So, if you are using the big size balls which can reduce the particle size faster And if you are using these small size balls, so which can achieve the finer and uniform results. So when you are using the big size balls, it can reduce the particle size in a faster rate, and these smaller size balls will be helpful for making the fine size particle. And third one is hardness. So if you are using these harder media, that is the harder balls, so what happens is it can significantly improve the milling, it can efficiently mill the material, and it can reduce the contamination. And fourth one is the composition. So selecting the right ball, for example metallic balls or the non-metallic balls, you have to select the right ball, so with respect to the particular material, then only you can get the best results without any contamination of the material. So the final one is the cost. If you are using these high cost media, higher cost balls, what happens is you get a better graining performance, but the problem is it will lead to the increase the final cost of the product. The next important parameter is the rotational speed, and here with the increased rotation speed, what happens is it will produce the greater transmission of energy to the powder and milling media, and the speed of the ball is expressed as the percentage of critical speed, and critical speed is the speed at which centrifugal force is high enough that all balls stick to the mill wall during rotation of the mill. So the critical speed means at a particular speed, so all the balls will be stick to the mill wall, but at this condition your grinding efficiency will be less. So for that we have to reduce the critical speed, so that is called your normal operating speed, which is about 75% of your critical speed. And how we can calculate the critical rotational speed? So by using this formula we can calculate the critical rotational speed, and here this R denotes the radius of your cylinder, that is your milling container, and this R denotes the radius of the your milling media, that is the balls, and G denotes the gravitational force. So if you are using this high speed, so as I told earlier, at high speeds, so the balls will be held against the milling container wall due to the high centrifugal force and revolve with the mill. So in this case the grinding efficiency will be less, and in the case of low speed, attrition action will be more. That means the balls will be rubbing each other, the attrition action will be more, and at the optimum speed we will have the attrition plus impact. So balls will be taken by the centrifugal force and it will fall back and it will break the material. So that is the advantage of this rotational speed. We have to use the optimum speeds to achieve the smaller size particle. So the next important parameter is BPR ratio. BPR is ball to powder ratio. So this is one of the important parameter, because the powder transformation rate is mainly determined by BPR ratio. Generally we keep a higher ratio between the milling ball and the coarse powder, usually 15:1. For example, if you are using the 5 gram of powder, we have to use 75 gram of milling balls. So that is 15:1 ratio. If you are using that ratio, then you can get the smaller size particle. So the next important parameter is the vial filling volume, and to ensure the milling balls gain sufficient energy for impactful collision, so the vial is typically filled 1/2 or 1/3 of its capacity, so that it will get the empty space, so which allows the balls to move freely and which can generate a stronger impact and enhance the attrition process. So that is why you have to always keep this head space at least 1/3, it should be kept empty, so that the balls can freely move and it can create more impact as well as the attrition. So the last parameter is the milling duration. So the total time of material subject to milling, so it depends on the material, from it can go from few hours to few days, and also it depends on your material type, it can be depends on the material hardness, so it can also go from few hours to few days. So with respect to the time, the particle size will go down, and when the size goes down, you know the surface area to volume ratio will be higher. And what is the mechanism behind this ball milling, how it is making this coarse powder into nano size powder? The first stage is a squeezing stage, where overlapping of the powder particles happens, and the next stage is welding stage, where the particles will be joined together through the welding amongst each other, that is, will join together. And the third stage is the fracturing stage. Due to the impact as well as the compression, the powder will be flattened, and the crack will be initiated by due to the repeated uh, impact by the balls. And once the crack is initiated, then it's a due to the repeated hitting of balls to the material, so it will have the different kind of fragmented and the particles will be broken into small pieces, and finally what you get is the nano size fine powder. So that is the dynamic balance stage. I hope you understood the principle and theory of these ball milling techniques. Now let us move to the lab and see the practical demonstration to understand the technique more in detail. In this demonstration, we are going to synthesize nano powder through ball milling method. For that, we require our bulk material, which is Tragacanth gum. Here you can see the size of the bulk material. Next, we require 5 mm balls, 2 mm balls, tungsten carbide jar, spatula, a sieve for separating the powder and balls, glass petri dish, a mixer grinder, and tissue paper. First, we are going to grind the bulk material into a coarse powder using a mixer grinder. Now, we are going to weigh 5 grams of this coarse powder using a weighing balance. We have weighed 2 sets of powder. Next step is to weigh the balls. For that, we have 5 mm balls, you can see the size, and 2 mm balls, you can see the size. Here we are going to weigh 37.5 grams of zirconium oxide balls using a weighing balance. We have weighed 2 sets each of 2 mm balls and 5 mm balls. Next, in a tungsten carbide jar, we will add coarse powder, 2 mm balls and 5 mm balls. Close the jar properly and tighten the screw to secure it. Here we have prepared 2 jars with the same composition, which will be balanced while performing the process in the ball milling setup. This is the ball milling machine by which we are going to convert the coarse powder into the nano powder. So first turn on the machine, the door will open, and then we will place the jar inside the machine. Lift the handles, place the jar inside, push the button and press the jar into the space, then close the handles. Select jar number 2 and then repeat the same process. Then close the door. Now let us set the settings. We will set the speed at 400 rpm. Runtime will be 10 minutes for each cycle and 15 minutes pass for each cycle. We are setting a total of 75 cycles. This reverse option changes the rotation of the jars from anti-clockwise to clockwise and vice versa for efficient milling. After setting the parameters, press start to begin the process. When the process is completed, open the door, and now we can remove the jars one by one. Pressing the button lifts the jar up so that we can pull it out. Repeat the process for jar 2. And then turn off the machine. Now we will open the jar and take out the materials by unscrewing the cap first and then taking off the lid. Strain the material through a sieve to separate the balls from the nano powder. You can see that the balls are separated from the powder. So, in this demonstration, we have successfully converted a bulk material first into a coarse powder by using a mixer grinder, and then into a fine powder through the ball milling method. In this image, you can observe that the coarse powder of tragacanth gum, when added to water, forms a hydrogel despite dissolving. In contrast, the ball mill powder dissolves completely, indicating that the dissolution properties of tragacanth gum improve as the particle size decreases. At the same time, the hydrogel forming property of the material decreases. The scanning electron microscopic images of both the coarse powder and ball milled particles taken at the same magnification clearly shows the size reduction of ball milled tragacanth gum. When further magnified, the nano-sized particles of tragacanth gum becomes visible. In the transmission electron microscopic image of the ball milled nano-sized particles, the size of the particles is observed to be 35.54 nanometer. So, as a summary of this lecture, we have learned how to synthesize nanoparticles using ball milling, and we also learned what is the principle of ball milling and what are the various types of ball milling and what is the role of various process parameters in the ball milling. By a practical demonstration, we also learned the ball milling technique more in detail. Thank you for your kind attention. I will see you all in another interesting lecture.